Imagine you have like a massive stack of capital, and you want to invest it in the ultimate frontier space.
Right.
And if you approach this like a standard software investor, your first instinct is to, play the odds. You look at the dozens of aerospace startups out there, and you take that index fund approach.
Yeah, the classic spray and pray.
Exactly. You buy a little bit of everything. You assume that if just one of those companies becomes the next Tesla of the stars, the massive upside will easily cover the graveyard of failed startups in the rest of your portfolio.
I mean, it sounds perfectly rational on paper, right? That broad net approach is literally the foundation of modern venture capital. You expect a 90% failure rate.
Right, but out there in orbit, physics actively breaks the traditional venture capital playbook. You really can't pivot your way out of the laws of gravity.
No, you definitely cannot.
And throwing software money at hardware problems has historically been a total disaster. Like, by early 2026, the ARK InvestSpace Fund had lost nearly 80% of its value using that exact spray and pray strategy. The environment is just too unforgiving.
Which means the investment logic for the space economy has, it's completely inverted. We are seeing this hard pivot away from diversification. You have to look for singular, highly concentrated execution.
Okay, so you mean betting on one strong player?
Right. You are looking for a company that isn't just building a rocket, but engineering an entirely new, deeply integrated economic system around that rocket.
And that is exactly our mission for this deep dive today. We are unpacking a stack of really fascinating, highly detailed engineering analyses, along with the Q1 2026 financials for Rocket Lab. That's ticker symbol RKLB.
Yeah, and the sources on this one are wild.
They really are. We're going to decode how a company led by Peter Beck, a founder who, by the way, doesn't even have a college degree, is actively rewriting the aerospace rulebook.
It's pretty incredible. They really aren't trying to just copy SpaceX.
No, they're building a completely unique set of engineering modes.
Wow.
And we'll get into it, specifically around their upcoming Neutron rocket, the Archimedes engine, and this highly guarded carbon fiber technology.
The contrast here is just stark. I mean, if you look at the traditional aerospace industry, the legacy defense contractors, they operate like these massive, heavily armored dinosaurs.
Right.
They've dominated the landscape for decades simply because they were the only ones big enough to survive. But Rocket Lab is operating like a highly evolved, warm-blooded mammal.
I love that analogy. They're small, nimble, and basically quietly sneaking into the nest to steal the dinosaurs' eggs.
Exactly.
But, before we get into the actual thermodynamics of the rocket, we really have to look at the balance sheet.
Yeah.
Because you cannot build a contrarian, highly innovative rocket if you are trapped in legacy contracts. The money ultimately dictates the engineering.
It really does. And the legacy industry is deeply infected by what we can call the state-owned contractor disease.
Oh, the cost plus trap.
Yeah, this originates from the core structure of traditional government funding, the cost plus contract. Historically, the government used these to mitigate risk for companies building totally unknown technologies.
Make sure they don't go bankrupt trying to invent something new.
Right. So the government agrees to reimburse the company for every single dollar spent on development and manufacturing, plus a guaranteed fixed percentage of those total costs as pure profit.
Okay, so just so I have this straight, if you invent a valve for $10,000, you get a percentage of $10,000.
Yeah.
But if you say bloat the timeline, overcomplicate the design, and spend $1 million building that exact same valve, you get a percentage of $1 million.
You get a percentage of $1 million. The system mathematically punishes efficiency. It literally strips a company of its evolutionary drive.
Wow.
If you spend 40 years surviving in a cost-plus environment, you lose the ability to survive in the commercial wilderness. There is zero institutional incentive to innovate, simplify, or drive down costs.
Which means if that government funding ever dries up, those companies have no idea how to compete against a commercial upstart.
Not at all.
And looking at Rocket Lab's Q1 2026 numbers in our sources, they are swimming in the right kind of cash. They hit over $200 million in Q1 revenue with $2 billion in total liquidity.
It's a massive war chest.
Yeah, and a massive chunk of their backlog is actually coming from the defense sector. The analysis highlights a $190 million contract for an MCTB hypersonic test platform alongside this major space missile defense project with Raytheon.
And just to jump in here, I think it's important to frame how we're looking at this.
Right. And just to be completely clear for you listening, as we look at these defense contracts, we are analyzing this strictly through a financial and strategic lens. This is about tracking the cash flow and the business modes. It is absolutely not an endorsement of any political or military stance.
Exactly. Economically speaking, taking on these contracts is just a very calculated move.
Right. They are using that lucrative government cash to quietly fund a hyper-aggressive commercial roadmap. Instead of getting lazy on government money, they're pouring it into vertical integration.
They want to own every microscopic piece of the supply chain.
Yeah, like, for example, they acquired Motive. That's the engineering team that built the robotic arms for the Mars rover.
Right, so suddenly Rocket Lab isn't just a delivery truck for other people's satellites. They have the in-house capability to build the payload, launch the payload, and operate the payload.
And the vertical integration gets even more aggressive when you look at the international chessboard.
Yeah.
One of the acquisitions mentioned in the sources was a German laser communications company.
Yeah, that one is brilliant.
I mean, I have to ask, on the surface, a rocket manufacturer based in New Zealand and America buying a niche German laser firm seems entirely random. Why do that?
Right, it looks random. But if we pull back and look at the European Space Agency, the ESA, it becomes one of the smartest geopolitical hacks in modern aerospace.
Oh, because the ESA operates a closed loop.
Exactly.
I was reading about this in the sources. Their geographic return policy, it basically mandates that if a member state, say Germany, contributes 20% of the overall ESA budget, the ESA is legally required to award 20% of its manufacturing contracts back to German domestic companies.
Yeah, it's a massive protectionist wall.
So an American company couldn't bid on those contracts, even if their tech was 100 times better and half the price.
It is an impenetrable barrier for outside commercial aerospace. But by acquiring that specific German laser company, Rocket Lab didn't just buy a technology stack, they bought a German passport.
Oh, wow.
They essentially purchased a Trojan horse that completely bypasses the geographic return policy. It grants them immediate, legally protected access to this highly insular European market.
That's wild.
Yeah, the French foreign minister actually flew out to tour their headquarters shortly after the strategy became apparent.
That transition from securing the funding and the market access to actually building the machine is where their contrarian philosophy gets physical.
It's where rubber meets the road. Or, well, carbon fiber.
Right. Once you bypass the bureaucracy, you have to bypass the legacy engineering. And nothing represents that better than the physical shape of their next generation vehicle, the Neutron rocket. If you look at every rocket for the last 60 years, they all look exactly the same. They're cylinders.
Just long, narrow tubes.
And we naturally assume they are cylinders for aerodynamic reasons,
Right.
to pierce the atmosphere efficiently.
But the truth is actually far more mundane. They are cylinders because of bridges and tunnels.
Wait, really? Which is an incredible constraint to put on space exploration. You're saying the physical shape of our entire space program was dictated by the diameter of highway overpasses.
I mean, yeah. Historically, major aerospace manufacturing facilities were built deep inland, mostly for strategic security during the Cold War.
Okay, that makes sense.
But orbital mechanics dictate that you must launch rockets near the coast, usually over the ocean, so that the drop stages don't land on populated areas. So the core engineering problem was never just getting to space.
It was getting to the launch pad.
Exactly. It was getting the rocket from the factory in the middle of the country to the launch pad on the coast. You had to put it on a truck or a train. It had to clear mountain tunnels and highway bridges. Human transportation infrastructure literally became the ultimate bottleneck for rocket design.
So Rocket Lab just looked at that bottleneck and refused to play the game.
Pretty much. They are building their Neutron manufacturing facilities directly at the launch sites.
Right. They have facilities in New Zealand and at Wallops Island, Virginia, where the factory doors practically open up onto the launch pad.
Which frees them entirely from the tyranny of the cylinder. Without the need for road transport, Neutron doesn't have to be a narrow tube. It is designed as a cone.
Yeah, it has a significantly wider, fatter base that tapers up to the nose. It looks like a giant shuttlecock or like a closed parachute.
And that wide base serves a massive aerodynamic purpose when the rocket is coming back down to Earth. This brings in the physics of reentry and a really critical metric called the ballistic coefficient.
Okay, break that down for us.
So when a rocket's first stage completes its job and falls back into the atmosphere from a suborbital trajectory, it is traveling at horrific speeds, often upwards of 7,000 to 8,000 kilometers an hour.
Wow.
And the friction generated against the thickening atmosphere creates heat that will instantly melt traditional aerospace alloys.
Which is why the SpaceX Falcon 9 requires that massive fuel-heavy re-entry burn just to survive, right?
Yeah.
It has to reignite its engines and fire them against its direction of travel to slam on the brakes before it hits the thickest part of the atmosphere.
Right. But carrying that extra fuel for a reentry burn is a massive economic penalty. Every kilogram of fuel you reserve for the trip home is a kilogram of payload you cannot sell to a customer.
Ah, I see.
Because Neutron is a wide cone, its massive bottom surface area radically alters its aerodynamic profile. It has a very low ballistic coefficient. When it hits the atmosphere, that huge flat bottom generates immense natural drag. The shape itself acts as a passive braking system.
So by the time Neutron drops down to, what, about 20 kilometers above the Earth, where the air is the most punishing, it is naturally bled off a massive amount of speed.
Exactly.
So it acts more like a heavy glider, mitigating that extreme heat of atmospheric friction without needing to waste payload capacity on a huge re-entry fuel reserve.
But even with those aerodynamic brakes, the friction still generates incredible heat. And this leads us to the core of their materials science moat. To make a lightweight, reusable vehicle, Neutron is constructed primarily out of carbon fiber.
And whenever we talk about carbon fiber in extreme pressure environments, we definitely have to address the elephant in the room. The Titan submersible disaster put a massive spotlight on the catastrophic failure modes of carbon fiber.
Yeah, everyone saw that.
We saw what happens when we put a carbon fiber tube under extreme pressure. It shattered instantly. So if I'm a telecommunications company looking to put a $100 million satellite on top of a giant carbon fiber tube filled with highly explosive rocket fuel, I might be a little hesitant.
It is a very common concern. But it stems from fundamentally misunderstanding the forces at play.
Oh, so?
Well, the physics of a deep-sea submarine and the physics of an orbital rocket fuel tank are diametrically opposed. A submarine sitting miles underwater is fighting immense compression.
Because the entire weight of the ocean is trying to crush it inward.
Right. And carbon fiber is highly vulnerable to compression. If the structure deflects inward, even on a microscopic scale, you lose structural integrity and suffer an instant catastrophic implosion.
But a rocket fuel tank isn't fighting the weight of the ocean.
No, it is fighting internal pressure, pushing outward. It faces tension.
Yeah.
And carbon fiber has astonishing tensile strength. It actually benefits from what engineers call hoop stress.
Yeah, in the sources, there was this great analogy. It behaves almost exactly like an unopened can of soda.
Yeah.
If you take an empty aluminum can, it is incredibly flimsy. You can crush it with 2 fingers. But if that can is sealed and full of carbonated liquid, that slight internal pressure pushing outward creates hoop stress. It makes the thin aluminum shell incredibly rigid, to the point where you could literally stand on it.
Yeah, the rocket fuel is doing the exact same thing to the carbon fiber shell, giving it immense structural rigidity.
And we also have to dispel the myth of what is actually happening inside that fuel tank during launch. Right?
Oh, absolutely. You watch a rocket lift off, you see the blinding pillar of fire coming out the back, and you naturally assume the fuel tank sitting right above that fire is a high-pressure bomb waiting to go off.
But the tank itself is surprisingly lazy.
Incredibly lazy. The combustion chamber at the very bottom of the engine is a high-pressure nightmare, operating at maybe 80 to 100 atmospheres of pressure. But the massive fuel tank taking up the bulk of the rocket, it typically only sits at about 3 to 5 atmospheres of internal pressure.
Just sitting there like a soda can.
Right. The unsung heroes making that work are the turbopumps. They sit right between the low-pressure fuel tank and the high-pressure combustion chamber. They draw down that lazy, low-pressure fuel, spin it up violently, and slam it into the combustion chamber at extreme pressure. The tank itself is entirely isolated from the blast.
Okay, so if catastrophic explosion isn't the primary threat to a carbon fiber rocket, what is keeping their materials scientists awake at night?
The true enemy of reusable carbon fiber rockets is a phenomenon known in the industry as LBB, leak before break, and it is driven entirely by thermal shock.
Just the temperature swings.
Yeah, the environment a reusable rocket operates in is a thermodynamic nightmare. The liquid oxygen loaded into the tank sits at negative 180 degrees Celsius. It is deeply cryogenic, but just minutes later during launch and re-entry, the outside of that exact same carbon fiber wall can hit 300 degrees Celsius.
Those temperature swings are violent, and basic physics tells us that things contract when they freeze and expand when they burn.
Exactly, but the carbon fiber threads themselves are actually quite resilient to thermal expansion. The weak link is the glue that holds those threads together, the epoxy resin.
Ah, the resin.
Standard aerospace epoxy is slightly hygroscopic, meaning it absorbs trace amounts of water molecules from the ambient air. So when you flood the tank with cryogenic liquid oxygen, that trapped water instantly freezes and expands, fracturing the resin from the inside out.
And then you launch it, exposing it to 300-degree heat and intense vibration, which just rips those microscopic fractures wide open.
Right. The rocket won't necessarily explode, but you end up with millions of microcracks. The carbon fiber literally starts to sweat highly flammable liquid oxygen through the walls of the rocket.
And if your orbital vehicle is sweating liquid oxygen on the launch pad, that asset is permanently grounded. You have lost the reusability game.
Completely.
So to solve this, Rocket Lab had developed a highly guarded chemical trade secret. The sources actually refer to it as their dark tech.
Sounds ominous.
It does. They abandoned standard epoxy resins entirely and engineered specialized cyanate ester resins.
Which sounds incredibly complex to manufacture.
From what the analysis says, it is downright hostile to manufacture. Synthesizing cyanate esters requires handling highly toxic, lethal precursor chemicals like cyanogen chloride, and the reaction has to be perfectly controlled at freezing temperatures. It is not something you casually brew in a standard facility.
But the payoff for that chemical nightmare happens when they actually apply it to the carbon fiber and bake it, right?
Exactly. When they cure this resin in an oven at temperatures between 150 and 250 degrees Celsius, it undergoes this chemical transformation called cyclotrimerization.
It is a brilliant piece of molecular engineering. During that intense heat cure, the long molecular chains of the resin cross-link. 3 separate chains will find each other and bond into a tightly locked, 3-dimensional hexagonal shape known as a triazine ring.
Okay, so it locks together.
Yeah, and when you multiply that reaction by billions, the resin forms a microscopic, highly dense honeycomb structure.
And because that honeycomb is so incredibly dense, it physically blocks water molecules from entering the matrix. It pushes the glass transition temperature, the point where the resin starts to soften and fail up past 300 degrees Celsius, so it can survive both the cryogenic fuel and the friction of reentry.
But the engineering goes one step further. Even with that perfect triazine honeycomb, the acoustic shock and vibration of launching a rocket could still initiate a microcrack.
So what do?
They embed nano-toughening agents directly into the resin. They are essentially mixing microscopic, squishy, rubber-like nanoparticles into this ultra-hard, glass-like resin.
Putting rubber in a rocket shell sounds completely counterintuitive to me, but the mechanism is fascinating.
It really is.
Because if a microcrack starts to tear through that hard honeycomb structure, it is carrying a tiny amount of strain energy.
Yeah.
But eventually that crack hits one of these rubber nanoparticles.
Right, and because the rubber is pliable, it acts like a microscopic shock absorber. It absorbs the tearing energy, squishes, and physically arrests the crack dead in its tracks. It stops the damage at the molecular level before it can spread. That combination of cyanate ester resins and nano-toughening agents creates a material that can theoretically be flown, frozen, heated, and flown again indefinitely without sweating fuel.
But having a beaker of perfect resin in a chemistry lab doesn't get you to space. You still have to build a 43-meter-tall orbital launch vehicle out of the stuff.
Yeah, and you have to do it without leaving a single microscopic air bubble in the layup. Because if there is a gap in the carbon fiber, the pressure will absolutely find it.
This is where their manufacturing process becomes a mode of its own. You cannot lay this material by hand. They utilize AFP, or automated fiber placement.
And the scale of this machine is wild. It's a massive robotic arm that moves at 100 meters per minute, laying down ribbons of this specialized carbon fiber tape over a rotating mold.
And it isn't just dropping tape, it's heating it, applying precise pressure, and most importantly, inspecting it.
Right. There is a millimeter-level camera system monitored by an AI running right behind the applicator head. It is utilizing advanced profilometry to scan the topography of the carbon fiber in real time as it goes down.
I love the comparison the sources made for this. It's like having a robot typing a novel at light speed, while an AI spell checker follows a millimeter behind, scanning every single comma and period.
It's exactly like that.
If it detects a flaw, a gap, or a microscopic bubble, it stops the machine and corrects it instantly. It completely removes the human error from the physical construction of the rocket.
That obsession with manufacturing reliability over raw, bleeding-edge performance doesn't just stop at the carbon fiber shell, though. It is the exact same philosophy that drove the design of their engine, the Archimedes.
Oh, Archimedes.
Yeah.
That is where Peter Beck had to publicly eat his own hat.
Literally.
He famously swore he would never build a liquid rocket engine of this scale. And when he finally did, he put his hat in a blender and ate it on a live stream.
You have to respect a CEO who actually follows through on that.
Right. But currently, SpaceX commands the industry respect for their Raptor engine. The Raptor is an engineering marvel. It uses a full-flow staged combustion cycle.
It pushes the absolute boundaries of thermodynamics to wring out every last fraction of a percent of efficiency from the fuel.
But Rocket Lab intentionally stepped back from that cliff edge. They designed Archimedes using a much simpler, oxidizer-rich, staged combustion cycle. So I have to ask, why would you deliberately engineer an engine that is fundamentally less efficient than your primary competitors?
It all comes down to the reusability matrix. A full-flow staged combustion cycle like the Raptor is brilliant, but it is incredibly complex. It requires two separate preburners, one running fuel-rich and one running oxidizer-rich to drive the turbopumps. That means you are managing two separate extreme pressure infernos before the fuel even reaches the main combustion chamber. The plumbing is labyrinthine, and the operating pressures inside those turbines are astronomical. If a seal is off by a fraction of a millimeter, the engine obliterates itself.
So you are operating on a razor's edge just to get a tiny bump in payload efficiency.
Exactly. By choosing an oxidizer-rich staged combustion cycle for Archimedes, Rocket Lab only uses one preburner. They immediately cut the most complex plumbing on the engine in half.
Wow.
Yes, they sacrifice a few percentage points of peak-specific impulse. The engine is technically less efficient, but by stepping back from the absolute limits of physics, they drastically lower the operating temperatures and pressures on the turbopumps. They reduce the thermal stress on the entire system.
It is the art of commercial compromise. The goal for Archimedes isn't to set a thermodynamic record or, win an engineering purity award. The goal is an engine that can be fired, recovered, and fired again 20 times in a row without needing a team of PhDs to meticulously rebuild the turbopumps after every single flight. It is designed to be an absolute commercial workhorse.
And that focus on commercial utility extends to the very top of the rocket, too, with the Hungry Hippo fairing.
Hungry Hippo fairing, that's such a great name.
It perfectly describes it. Traditionally, the nose cone, the fairing that protects the satellite during launch, splits in half once the rocket reaches space, falls away and either burns up or drops into the ocean where a ship has to fish it out.
But Neutron's fairing doesn't detach. It is permanently fixed to the rocket. It opens up like a giant mouth, spits the satellite out into orbit, snaps back shut, and rides the rocket all the way back down to the landing pad.
Which completely solves the fairing recovery problem.
Yeah.
But if you think about the mechanics of a captive fairing, it unlocks this massive secondary capability. If the rocket can open its mouth in orbit to spit things out,
it can open its mouth to take things in.
Exactly. Neutron has the capability to rendezvous with a dead satellite or a massive piece of dangerous orbital debris, open that fairing, swallow the debris, and safely glide it back down to Earth. It basically becomes the ultimate orbital sanitation vehicle.
Which perfectly synthesizes Rocket Lab's entire operational philosophy. The spray-and-pray investment strategy failed because you cannot stumble into this level of integration by accident. Every single choice they make is interlocked to build an impenetrable business moat.
It really is all connected.
They secure their cash flow with legacy contracts. They strategically acquire their supply chain to bypass geopolitical red tape. They abandon the cylinder to optimize for glide reentry. They engineer molecular-level carbon fiber to solve thermal cracking. And they choose engine reliability over explosive power.
It is a masterclass in holistic engineering. They aren't just solving for thrust, They are solving for economics.
Which leaves us with a pretty profound structural question for you to mull over as we end today. If this one private company manages to vertically integrate absolutely everything, if they're building the rovers that sample Mars, manufacturing the rockets on site, synthesizing their own resins, cleaning up orbital debris, and eventually launching their own global satellite networks, what happens to the balance of power?
It's a heavy thought.
It is. We're moving incredibly fast from an era where sovereign nations and massive government agencies govern the stars to an era where a few highly efficient, commercially driven tech oligarchies might become the true rule makers of human space infrastructure. Keep an eye on the sky because the rules of gravity and economics are rapidly shifting.